electrode potentials and cells, half cells. This topic is very, very difficult. Not too much content, but exam style questions are pretty difficult. So first things first, electrochemical cell made from two different metals dipped in salt solutions of their own ions connected by wire, aka the external circuit. Wire reaction within electrochemical cells redox, one oxidation, one reduction, always two reactions in electrochemical cell. Electrons flow through wire from more reactive metal to less reactive metal. A voltmeter in external circuit shows a voltage between two half cells. The EMF or electromotive force any given time shows a voltage between two half cells. Voltmeter. Have half cells involving solutions. Examples of half cells involving solutions of two aqueous ions of the same element. An example of this is a conversion from Fe2 plus to Fe3 plus, and this happens on specifically the surface of the platinum electrode. Why is it platinum? Because the electrode made of platinum is inert metal, therefore won't react with ions. Classic question could be asked, so definitely learn that. Then you got zinc solid, Zn2 plus aqueous, Cu solid, Cu2 plus aqueous, and then you've got that's your salt bridge. That's your external circuit bracket, your wire. Solutions are connected by a salt bridge. And what is a salt bridge made of? Made from filter paper soaked in HNO3 aqueous, KNO3 aqueous, sorry. Solutions connected by salt bridge made from filter paper soaked in KNO3 aqueous. And salt bridge allows ions to flow through and balance out the charges. Now, zinc loses electrons more easily than copper. Therefore, the zinc from the zinc electrode is oxidized to Zn2 plus aqueous, releasing electrons external circuits, and the other half cell, same number of electrons taken from external circuits, reducing the Cu2 plus ions to copper atoms. When you write a half equation for electrochemical cells, the reduction is always in the forward direction with the electrons on the left-hand side. When two half cells are joined to make a cell, what happens? The direction each reaction goes depends on how easily a metal loses an electron. And this is aka how easily metals oxidize, and is measured using electrode potentials. Metal that's easy to oxidize has a very negative that EMF. Metal harder to oxidize has a less negative EMF voltmeter. Electrode potentials measured against a standard hydrogen electrode. Standard electrode potential of a half cell. The voltage measured under standard conditions when a half cell connected to a standard hydrogen electrode. The voltage measured under standard conditions when half cell connected to a standard hydrogen electrode. Any solution must have a concentration 1 mole per DM minus cubed. If standard conditions are maintained, the reading of voltmeter when half cell connected to standard hydrogen electrode would be standard electrode potential of the half cell. Electrochemical series. A list of standard electrode potentials for different electrochemical half cells. A list of standard electrode potentials for different electrochemical half cells. More positive electrode, therefore the left-hand side substances are easily reduced. The right-hand side substances more stable. More negative electrode, and the right-hand side substances are easily oxidized. Left-hand side substances more stable. Use standard electrode potential values to calculate EMF when two half cells join together. Standard cell potential. Always remember the most positive potential minus the most negative potential. So, for example, if I'm given two electrode potential values and I want to calculate the EMF standard cell potential when two half cells join together, and the exam gives me minus 0.46 for one, 0.42 for the other, I would do 0.42 minus 0.46. So I'd always do the more positive potential minus the most negative potential. Now, if it's not directly positive and negative, then what you would do, so for example, if it's 1.5 or 1.3, then you do what's the most positive? 1.5 minus 1.3. That's really, really important that you just memorize that key fact, because in an exam question, then you know which one you're subtracting. Because if you get it the other way wrong and you mix them two, you're not going to get the mark, or maybe the marks. So yeah, raw, reduced form, oxidized form, reduced form. Key points. Things in different phases are separated by a vertical line. So you can see that vertical line, aqueous, solid, whatever. Things in different phases separated by a vertical line. Double vertical lines show a salt bridge. And remember, the salt bridge, solutions connected by a salt bridge made from filter paper soaked in KNO3 aqueous. Allows ions to flow through and balance out the charges. And half cell with more negative potential goes on left hand side of raw. That's also really important. Half cell more negative electrode with more negative potential on left of raw, and oxidized forms go in the center of the cell diagram. Batteries. Types of electrochemical cell providing electricity to power watches/mobile phones. Some types of cells are rechargeable while others only be used when they run out. Non-rechargeable batteries cheaper than rechargeable ones, but we can just recharge/reuse rechargeable batteries, therefore they last longer and cheaper in long run. Electrochemical cells are used as batteries. Lithium batteries are rechargeable batteries found in mobile phones, laptops, and cars. Lithium cells used in mobile phones/laptops. One type of lithium cell is made up of a lithium cobalt oxide electrode and graphite electrode. Electrolyte is a lithium salt in an organic solvent. And you need to know these half equations. At the negative electrode, Li arrow Li plus E minus. A positive electrode, Li plus COO2 plus E minus arrow Li plus COO2 minus. In square brackets, remember, right, Iman, that's really easy. It is, right? Just memorizing these two equations, obviously, and all of the other content. But there are many other examples which aren't actually on the specification, but they could come up, and I've seen my teacher said there was a question on it, so I probably will go through those as well. Reaction of non-rechargeable batteries are difficult/impossible to reverse. How to recharge these batteries? Current supplies to force electrons to flow in the opposite direction around the circuit and reverse the reactions. Current supplied. So if the electrons going this way, I want to recharge the batteries. The current supplied to force the electrons to flow in the opposite direction around the circuits and reverse these reactions. Reverse reactions. Fuel cells generate electricity from water, hydrogen, and oxygen. Overall reaction 2H2 gases plus O2 gases form 2H2O gaseous. Fuel cell chemicals stored separately outside the cell and fed in when electricity is required. Example, alkaline hydrogen oxygen fuel cell used to power electric vehicles. Hydrogen oxygen gas is fed into two separate platinum containing electrodes. Electrodes separated by anion exchange membrane, allowing anions and water to pass through it, but not hydrogen oxygen gas. Electrolyte equals aqueous alkaline potassium hydroxide solution. Hydrogen fed to negative electrode, 2H2 gases plus 4H minus aqueous arrow 4H2 liquid, 4H2O liquid plus 4E minus. Oxygen fed to positive electrode, O2 gases plus 2H2O liquid plus E minus arrow 4OH minus aqueous. Electrons flow from negative electrode through external circuit to positive electrode. Makes sense. OH minus ions pass through anion exchange membrane to negative electrode. OH minus ions pass through anion exchange membrane to negative electrode. Fuel cells in cars. More efficient compared to internal combustion engines. Converts more available energy, kinetic energy, gets car moving. The only waste product is water, no toxic chemicals to be disposed of, plus no carbon dioxide emissions released, right? Don't need to be recharged like batteries as long as hydrogen and oxygen is supplied. The cell produces electricity. Now, a couple of disadvantages which I don't write down, but hydrogen, extremely flammable, so to transport that, produce that, wherever it may be, you have to take it with care and maybe special equipment. So that's one. Another one is that the idea that yes, the only waste product is water. Yes, no CO2 emissions released, but in order to produce, this hydrogen and oxygen and all of that, you need to obviously undergo a reaction, and that reaction involves burning fossil fuels. So even though it is, I guess, in this case, carbon neutral, it's not really carbon neutral because of that idea that it's still going to release some CO2 to make the hydrogen and oxygen or to transport it, etc., etc. And this is really similar to the year one, and it was about bioethanol. Is the idea of, is it carbon neutral or not? And they really like to assess that. So